wherever you are right now, assuming you are indoors, just take a second and look up at the ceiling.
Yeah, just kind of scan it for a moment.
Right, because chances are, unless you are in a very old residential home, you are going to spot a small, unassuming metal disc.
Right.
Or maybe a jagged little brass nozzle just poking out of the drywall.
Which is something you've probably walked under thousands of times without giving it a second thought.
Exactly. But today, our mission for this deep dive is to completely demystify that tiny piece of hardware. We are exploring the hidden, highly engineered world of automatic sprinkler systems.
It's a fascinating topic.
Really is. We are going to look at the incredible physics of how they actually know a fire is happening, and we're going to break down the surprisingly tactical playbook that firefighters use when they have to interact with them in an emergency.
Yeah, because it really is a massive hidden ecosystem constantly operating right over our heads. And we are pulling back the curtain on this today using some very specific source material.
Right. What are we looking at?
Well, we are breaking down these heavy-duty engineering textbooks focused on community risk reduction and pairing those with the actual specialized performance objectives.
Oh, like the firefighter manuals.
Exactly. The step-by-step tactical checklists that firefighters are graded on during their training.
Yeah.
I mean, it gives us a complete view of both the hidden mechanics behind the walls and the human intervention required when chaos breaks out.
Which is so critical because, these things are everywhere, and yet our public understanding of them is just completely warped. And I blame Hollywood action movies 100% for this.
Oh, absolutely. The movies ruin it.
Right. Every single thriller has that scene where the hero holds a lighter up to a single sprinkler head in a hallway, and suddenly, boom, every sprinkler in the entire 50-story skyscraper starts blasting water at the exact same time.
It makes for a great visual, for sure.
It does, but my understanding from looking at these textbooks is that it is practically a fairy tale.
It is a complete myth. And honestly, it's kind of a dangerous one because it makes building owners and the public deeply distrust the system. Like, they worry that a minor accident will just flood their entire property.
Which makes sense if you believe the movies.
Right. But the engineering manuals established a foundational truth right from page 1. Automatic sprinkler systems are recognized as the absolute most reliable of all fire protection devices.
Wow, really?
Yeah, they almost never fail. And when we look at the mechanics of how they actually operate, the reality completely dismantles that whole Hollywood trope.
Okay, let's unpack this. Because before we even talk about how thousands of gallons of water travel through the building, we have to talk about the micromechanics.
Trigger itself.
Yeah. How does that tiny sentry on your ceiling actually decide to release the water? I know it's heat, right? Not smoke. But how does it know the heat is dangerous?
Well, the crucial concept to grasp here is that these are fixed spray nozzles opened individually by heat. Yes. There is no central computer, and there is no master switch that activates the whole floor. The underlying philosophy of this design is just pure risk management.
So you don't ruin the whole building.
Exactly. By having them open individually, you prevent catastrophic, unnecessary water damage, and you focus the building's entire municipal water pressure exactly, and only where the fire is currently burning.
So if a fire breaks out in the copy room, only the copy room gets wet. The servers down the hall stay bone dry.
That's the goal, yeah.
But how does the sprinkler actually trigger itself? I noticed the sources kept mentioning 3 different mechanisms, and the most common one involves like a tiny glass vial. I think it's called a frangible bulb.
Yeah, the frangible bulb. It is a masterclass in using basic physics for life safety.
How so?
Inside that little glass bulb is a highly specific heat-sensitive liquid, along with a tiny air bubble.
Just a little bubble.
Right. So during a fire, the ambient heat at the ceiling level rises, transferring energy into the glass and warming the liquid inside. As that liquid heats up, it expands.
Oh, I see where this is going.
Yeah, the tiny air bubble gets compressed until it just disappears, and the internal hydrostatic pressure inside that glass bulb just keeps building and building.
Until it can't take it anymore.
Exactly. Once the ambient room temperature hits a precise pre-calculated degree, the pressure exceeds the tensile strength of the glass. The bulb physically shatters.
Wow. It's basically a highly calibrated little grenade of physics.
That's a great way to put it. The glass breaks, the plug holding the water back falls away, and the water flows.
But not all of them use glass, right? I was reading about something called a fusible link, which sounds a lot more mechanical.
It is. The fusible link relies on the metallurgy of solder rather than an expanding liquid.
Okay, how does that work?
Picture the cap holding the water back being pinned in place by two small metal levers. Those levers are under constant tension, trying to push outward, but they are fused together by a link made of a specialized metal alloy, the solder.
So it melts.
Right. This alloy is engineered to melt at a very specific temperature limit. The moment the heat reaches that limit, the solder turns to liquid, the link separates, the levers fly apart, the cap drops, and the water is released.
That's brilliant.
And there is a third variation called the chemical pellet, which uses the exact same principle.
Yeah.
A plunger holds the valve cap closed, resting on a tiny pellet of solder. Heat melts the pellet, the plunger gives way, and the system activates.
But not all fires are the same, and not all environments are the same. Like a normal day near the ceiling of an industrial bakery is going to be way hotter than a normal day in a residential living room.
Oh, absolutely.
So how do firefighters or building inspectors tell what temperature a specific sprinkler is rated for just by looking at it?
Well, engineers use visual indicators. For a fusible link or chemical pellet, they will often color code the metal frame of the sprinkler itself.
Oh, okay. And for the glass ones?
For a frangible bulb, they actually dye the expanding liquid inside the glass. An orange or red liquid means it will shatter at a relatively standard temperature, say around 135 to 170 degrees Fahrenheit.
And if it's a hotter room?
Then you'd look for a green or blue liquid. That means the sprinkler is engineered for a high temperature environment and won't trigger until it gets much hotter. Or, in many cases, they bypass color entirely and just physically stamp the temperature rating directly onto the metal.
Makes sense. I also noticed they don't all point the same way on the ceiling. The sources kept referring to different orientations. Why does the direction they point matter so much?
It entirely changes the geometry of how the water is distributed.
Really?
Yeah. You have upright sprinklers, which actually sit on top of the pipe and shoot the water straight up against the deflector plate.
Up! Why up?
The deflector forces the water to fan out and crash down in a hemispherical pattern. You cannot just flip an upright sprinkler upside down. I mean, it just won't work.
Okay, got it.
Then you have the pendant orientation. That's the one most people recognize. It hangs down below the pipe and uses a differently shaped deflector to break the water stream into a circular, umbrella-like pattern of small droplets.
And I imagine architects want to hide these as much as possible in fancy spaces.
Absolutely, yeah. You will see sidewall sprinklers mounted high on the walls in hotel corridors where running pipes through the ceiling is just impractical.
Oh, I've seen those.
And for purely aesthetic reasons, modern buildings frequently use flush, concealed, or recessed heads. These physically hide the mechanical parts and the deflector above the ceiling drywall, covering them with a flat, decorative plate.
But doesn't that block the heat?
No, because that cover plate is soldered on. When a fire starts, the heat melts the solder on the plate first, the plate falls away, dropping the sprinkler head down, and then the heat goes to work on the frangible bulb itself.
Oh, that's so clever. So we've built this perfect heat-seeking trigger. But a trigger is just a paperweight if it doesn't have explosive power behind it. Where does a building actually get the massive water pressure required to feed hundreds of these at once? I was trying to picture the hidden plumbing, and the best analogy I could come up with is the human cardiovascular system.
Actually, the cardiovascular model scales perfectly to how engineers design water distribution.
Right. So you have the main water supply coming from the city water main. That's your intake, maybe from a reservoir or a water tower.
Exactly.
That feeds into the building's riser, which is the massive vertical pipe running all the way from the basement to the roof. The riser is like the aorta, the biggest, thickest vessel carrying all the volume.
Spot on.
From the riser, the water branches horizontally on each floor into what the texts call cross mains. Those are your major arteries. And then from the cross mains, it branches out again into the branch lines, the smaller capillaries that actually connect to the individual sprinklers.
And a key detail there is that the pipe physically decreases in diameter the further out it goes.
Just like blood vessels.
Exactly. Artificially squeezing the water to maintain high pressure all the way to the very last sprinkler head in the farthest corner of the building.
That is wild.
Maintaining that constant volume and pressure is really the central engineering challenge here. If the city water main drops in pressure, the whole system goes into shock.
So what happens then?
That is why many large buildings have dedicated fire pumps. They can be driven by massive electric motors, diesel engines, or sometimes even steam.
Just sitting in the basement.
Just waiting. Their sole function is to monitor the pressure in the riser. The instant a sprinkler head pops and the system pressure drops below a predetermined threshold, that internal pump violently kicks on.
Wow.
It starts sucking water from the city main and forcing it through those internal arteries to ensure the sprinklers don't just drizzle, but actually suppress the fire.
Wait, let me push back on that for a second. If a building has this massive dedicated diesel pump in the basement to ensure the pressure stays high, why do fire trucks always hook up to the building when they arrive?
Ah, good question.
You always see them connecting their giant hoses to those brass pipes sticking out of the brick on the side of the building. Isn't that totally redundant?
It's not redundant, it is a necessary failsafe, because internal systems can be overwhelmed. That brass pipe is called the fire department connection, or FDC.
FDC, okay.
Let's say the building's internal pump fails to start, or a massive fire opens 20 sprinkler heads at once, bleeding off pressure faster than the city main can supply it.
Right, the pump can't keep up.
Exactly.
Yeah.
The FDC allows a fire department's engine to act as an external mechanical heart bypass. What's fascinating here is how they merge the fire truck's power with a building's anatomy.
How does that work?
The fire engine drops a heavy intake hose to a street hydrant, uses its own massive 1,500 gallon per minute pump to vastly increase the pressure, and forces that water through hoses directly into the FDC. They are literally injecting municipal water into the building using the truck's engine power.
But wait, if the fire truck is blasting high-pressure water into the building, and the building already has water in its pipes, why doesn't the water just shoot backward out of the FDC onto the street when the fire truck disconnects?
Oh, that is handled by a brilliantly simple piece of internal hardware called a clapper valve.
A clapper valve?
It is essentially a one-way heavy metal door swinging on a hinge. When the fire truck pumps water in, the pressure pushes the heavy clapper door open, allowing water to flow into the building's riser.
And when they stop?
The moment the fire truck stops pumping, the pressure from the water inside the building slams that clapper door shut, sealing the pipe. It acts as a check valve, preventing backflow.
That's so simple but so effective.
And the sources also highlight a tiny unsung component near the FDC called the ball drip valve.
Ball drip valve, what does that do?
Its entire job is to let any leftover, lingering water in the FDC piping slowly drip out onto the ground when the system isn't being used. It keeps the intake pipe perfectly dry.
So it doesn't freeze?
Exactly. So that lingering water doesn't freeze into a solid block of ice during winter, which would block the fire truck from pumping water in.
And freezing brings us to the most frustrating part of these manuals. We established these systems are engineered to be hyper-reliable, so why do they ever fail?
It's unfortunate but true.
The textbook lists the primary reasons, and it is almost universally human error or environmental neglect.
The statistics are sobering, honestly. The hardware almost never fails on its own. Failure happens because a maintenance worker closed the main water control valve to fix a leak 6 months ago and forgot to reopen it.
Unbelievable.
Which essentially turns the entire system into empty metal tubes. Or it happens because a contractor painted the ceiling and accidentally painted over the sprinkler heads, creating a layer of insulation that stops the heat from reaching the frangible bulb.
So the bulb never gets hot enough to break.
Exactly. Or, to your point, the environment itself becomes the enemy and the pipes freeze and burst.
So how do you protect a space that is supposed to freeze? Say I'm an engineer protecting an unheated parking garage in Chicago in January.
Right. Tough scenario.
A standard setup, what the book calls a wet pipe system, where the pipes are completely full of pressurized water waiting to be released, would shatter into a million pieces the first night it dropped below 32 degrees.
It would be a disaster. For an environment that stays below 40 degrees Fahrenheit, engineers deploy a dry pipe system.
Dry pipe. Okay, how does that work?
In this configuration, the sprinkler heads are identical, but the pipes running through the unheated garage are completely empty of water. Instead, they are pumped full of highly pressurized air or nitrogen.
Wait, air?
Yeah, air. Down in the heated basement, there's a specialized dry pipe valve holding back the city water. The pressurized air in the pipes physically pushes down on that valve.
Oh, I see.
The air pressure acts like a giant invisible spring holding the water back.
Oh.
When a fire breaks out in the garage, the heat shatters the glass bulb on the ceiling. But instead of water coming out, the pressurized air hisses out first.
Releasing the pressure.
Exactly. As the air escapes, the pressure in the system drops. Down in the basement, the invisible air spring loses its strength, the main water valve pops open, and the water rushes up into the empty pipes and out of the open sprinkler head.
I see a huge flaw there, though.
That's that.
If the building is massive and you have hundreds of feet of piping filled with air, waiting for all that air to bleed out of a tiny half-inch sprinkler head could take several minutes.
You're not wrong.
A fire doubles in size every single minute. Waiting 3 minutes for water seems like a terrible, potentially fatal design.
Engineers recognize that lag time, which is why dry pipe systems over a certain capacity, usually 500 gallons of volume, require quick opening devices. They use components called accelerators or exhausters. Instead of waiting for the air to bleed out of the tiny sprinkler head, these devices actively monitor the internal pipe pressure.
So they speed it up.
Big time. The millisecond they sense a pressure drop, they open large exhaust valves, actively dumping the air out of the pipes in massive volumes. This allows the water to rush through the system almost as fast as a wet pipe system.
That's ingenious.
And furthermore, all the pipes in a dry system must be pitched, meaning they are installed at a slight slope.
Oh, so the water drains out afterward.
Exactly. After the system activates and the fire is out, that slope ensures every single drop of water drains back down to a central point, leaving the pipes completely empty again so they don't freeze the next night.
Okay, what if the hazard isn't freezing temperatures? What if the hazard is something so dangerous, so violently flammable, that waiting even for a single sprinkler head to pop is just too slow, like an aircraft hangar full of jet fuel or a chemical plant?
That scenario demands a deluge system. And a deluge system actually functions exactly the way Hollywood pretends all sprinklers function.
Wait, really? So a lighter would set off the whole hangar?
Essentially, yes. In a deluge system, the pipes are empty of water, just like a dry pipe system. But crucially, the sprinkler heads themselves do not have frangible bulbs or fusible links.
So what are they?
They are just wide open nozzles, all of them, all the time. The water is held back at the riser by a massive deluge valve. This valve is wired to a completely independent network of highly sensitive fire, smoke, or flame detectors spaced throughout the hangar.
Oh, so the detectors do the work.
Right. If those sensors detect a sudden spike in heat or the specific ultraviolet signature of a flame, they electronically trip the deluge valve. Water rushes into the pipe network and instantly blasts out of every single sprinkler head in the entire building simultaneously.
That must be terrifying to watch.
It is. The philosophy, it's a total saturation. You utterly drown the high hazard area before the jet fuel has a chance to fully ignite.
But then you have the complete opposite extreme. What if the building isn't a hangar, but a multi-million-dollar data center or a museum archive holding priceless original manuscripts?
Where water is just as bad as fire.
Exactly. You desperately need fire protection, but an accidental bump of a glass sprinkler bulb with a worker's ladder could dump thousands of gallons of water, causing millions in irreversible damage.
It's a huge concern.
The solution in the textbook for this is called a pre-action system. When I read how this worked, I immediately thought of it as like two-factor authentication for water release.
That two-factor authentication model is the perfect way to understand a pre-action system. It deliberately layers safety mechanisms to prevent accidental discharge.
Right, because a pre-action system uses closed sprinkler heads with glass bulbs, just like a wet pipe system, but the pipes are totally empty of water, just like a dry pipe system.
Exactly.
So if someone accidentally knocks the glass bulb off a sprinkler head with a broom handle, absolutely nothing happens. No water flows out because there's no water in the pipe.
It's fail-safe.
The system only arms itself, meaning it only opens the main valve to let water fill the overhead pipes if an entirely separate, independent smoke detector goes off in the room. But even then, the water still doesn't spray.
Right, it just sits there.
It just sits in the pipes, armed and waiting. The water will only actually discharge if the heat of the fire then rises high enough to physically shatter the glass bulb on that specific sprinkler head. The system demands two totally separate proofs of a fire before it commits to water damage.
It really illustrates the constant tightrope walk of risk management. Engineers must balance the catastrophic risk of a fire against the severe secondary risk of water damage.
Yeah.
You see this heavily in massive warehouse environments too, with in-rack sprinklers.
What are those?
If you have a warehouse with storage racks stacked 40 feet high, ceiling sprinklers are completely inadequate. The water simply cannot penetrate down through 40 feet of cardboard boxes to reach a fire on the bottom shelf.
That makes total sense. So what do?
You have to weave a network of pipes and sprinklers directly into the metal shelving framework itself.
But wait, if a fire starts on the ground floor, wouldn't the heat rise to the ceiling, pop the ceiling sprinklers first, and send freezing cold water raining down on the racks?
Yes, it would.
But then that cold water would hit the sprinklers mounted lower down on the shelves, cooling their glass bulbs off and completely preventing them from activating, even though the fire is burning right next to them.
That dynamic is exactly why in-rack sprinklers look different. Every single in-rack sprinkler is equipped with a physical protective metal disc. Think of it as a little metal umbrella mounted directly above the sprinkler head.
Oh, that's so smart.
When the ceiling sprinklers activate and rain down cold water, that umbrella shields the heat-sensing bulb underneath it, keeping it dry so it can still accurately read the ambient heat of the fire next to it and activate. Every single physical detail is calculated.
Okay, so the engineering has worked flawlessly. The system detected the fire, the right head's open, the pump engaged, the water flowed, and the fire is out.
Success.
But now you have hundreds of gallons of water pouring into the building every single minute. The emergency isn't over, it has just changed forms.
This brings us to the firefighter performance objectives.
Yeah. How do human beings actually interface with this technology in the middle of a disaster?
It requires a highly disciplined, almost surgical approach. Let's look first at how firefighters move their own water through a large structure, independent of the sprinklers. High-rise buildings are equipped with standpipe systems.
Standpipes, right.
Think of a standpipe as a massive, permanent fire hose built vertically into the stairwells of a building. Dragging hundreds of feet of heavy, water-filled fire hose up 10 flights of stairs is physically exhausting and far too slow.
I can't even imagine.
A standpipe allows firefighters to carry folded, empty hoses up the stairs, connect directly to a high-pressure outlet on the 10th floor, and immediately start fighting the fire.
And the texts specify different classes for these standpipes depending on who is supposed to use them, right?
Yes, exactly.
Like Class I systems feature massive 2.5-inch hose connections. The manuals make it clear those are strictly for trained fire suppression personnel because the water pressure is so intense it takes multiple firefighters just to hold the hose.
Right.
Class II systems use smaller 1.5-inch hose lines, often pre-connected on a wall rack. You see these in older buildings behind glass. They are designed for either trained occupants or firefighters to use for an initial response before the big engines arrive. And Class III systems combine features of both.
So the tactical infrastructure is in place. But if the sprinklers have already suppressed the fire, the immediate tactical priority shifts to water conservation.
Because it's flooding the building.
Exactly. The firefighter needs to physically plug the flowing sprinkler head to save the building from flooding. And the performance checklists we reviewed are incredibly strict about how this is initiated. A firefighter cannot just run into a smoky room and start twisting valves.
No, the training document outlines a rigid verbal checklist the firefighter must literally say out loud to their instructor before even touching the equipment.
Which is fascinating.
They have to say, I am in full PPE, I will notify the incident commander, I will notify the exterior and interior crews, I will work uphill and upwind, I will shut down utilities, and crucially, I will find a second means of egress.
Verbalizing those steps acts as a cognitive anchor. In a chaotic environment, with fire alarms screaming, heavy smoke reducing visibility to zero, and freezing water blasting down on you at 100 pounds per square inch, physically speaking, those safety checks forces the brain to slow down and process the tactical environment.
So the firefighter wades through the water, gets underneath the flowing sprinkler head. How do they actually stop the flow?
The manuals describe some amazingly physical analog tools.
Yeah.
One primary method uses wedges. It is literally two pieces of wood. You are fighting high-pressure water shooting into your face, and your job is to forcefully insert two wooden wedges into the metal frame of the sprinkler head, right between the arms, and slide them violently toward each other to create a makeshift cork.
That sounds intense.
It is. Alternatively, they use a specialized tool called sprinkler tongs. You push the tongs up into the frame, clamp the handles together to pinch off the water flow, and then you have to physically lock them in place.
How does it lock?
Depending on the design of the tongs, you either pull a metal ring called a keeper down the handles to bind them together, or you turn a locking knob clockwise to secure the clamp.
But the textbook makes a point to note that wedges and tongs are not perfect seals. Water is still going to leak around the wood.
Right, you can't stop it completely at the head.
So firefighters have to manage the runoff to protect the property below. They might build a catch-all, essentially folding a waterproof tarp into a temporary basin, or construct a water chute out of tarps to funnel the leaking water down a hallway and out a door.
Yeah, water management.
But my absolute favorite tactic in the manual is the most wonderfully low-tech, field-expedient solution imaginable. Here's where it gets really interesting.
The hose trick.
Yes. If a ceiling sprinkler is just gushing and wedges aren't working, a firefighter can take a standard piece of unrolled fire hose, hang one open end directly under the sprinkler head to catch the water like a giant canvas funnel, and then just unroll the rest of the hose out the nearest window. The water just flows through the hose and safely outside. It is brilliantly simple.
It is phenomenal field engineering. But, if you have multiple heads flowing, or the damage is too severe for tongs, the incident commander will order the entire system shut down.
Right.
This means sending a firefighter to locate the main control valves. The training specifies that firefighters must be able to visually recognize indicating valves from a distance, even through smoke.
What's an indicating valve?
An indicating valve physically shows you its status. You don't have to guess or turn it to find out if it's open.
And the acronyms for these are wild. First is the OS&Y, the outside stem and yoke valve. It works on a threaded stem mechanism. If the metal stem is sticking out inches beyond the control wheel, the valve is visibly open. If the stem is flush and hidden inside the wheel, it's closed.
Right.
Then you have the PIV, the post indicator valve. This is a hollow metal post sticking out of the ground in the landscaping outside the building. It has a small plexiglass window near the top with a physical sign inside that literally just reads open or shut.
You will also see the WPIV, which is simply the wall post indicator valve, acting exactly the same way, but mounted horizontally flat against the brick wall of the building.
Oh, crap.
And the PIVA, the post indicator valve assembly, this one doesn't use words. It uses a circular disc inside a flat viewing plate. When the disc is turned perpendicular, the valve is open. When the disc rotates to line up flat with the plate, it's closed.
Makes sense.
But before a firefighter puts a heavy pipe wrench on any of those valves or uses bolt cutters to snap the security chains holding them open, they must adhere to the absolute prime directive of the text.
Yes, the ultimate rule.
It is absolutely imperative to ensure the fire is completely, undoubtedly extinguished before closing that control valve.
Because if it's not,
It's a disaster. This represents the ultimate tension in the firefighter's playbook. They are actively trying to salvage the property from catastrophic water damage, but life safety and fire containment must always override property salvage. If a firefighter shuts that main control valve prematurely to save a carpet, and a hidden pocket of fire inside a wall flares back up, they have just manually disabled the building's only primary defense system. Fire will run rampant, and people could die.
So we have covered an incredible amount of ground today. We started by looking up at a tiny, fragile glass bulb filled with boiling liquid on the ceiling.
We really did.
And we have traced that trigger back through a massive, beautifully engineered cardiovascular network of specialized pipes, high-powered pumps, and municipal water mains. A system designed to sit silently in the dark for decades, waiting for a specific thermal threshold.
Exactly.
And then we layered on the human element, the calculated, physical, sometimes violent interventions required by firefighters to safely override and shut down that very same system. It is a profound intersection of automated physics and human judgment.
It truly is a silent vigilance. The building you are sitting in right now is likely quietly protecting you with these exact mechanisms.
Which leaves us with a final thought to ponder. Given everything we've unpacked today, given that stopping a sprinkler head requires a human being to fight through city traffic, don heavy gear, assess a chaotic situation, and then physically jam 2 wooden wedges into a metal frame while being blasted with freezing water, or manually crank a rusted OS&Y valve in an alleyway, consider this.
Yeah.
How much of modern fire damage to our buildings and our livelihoods isn't actually from the flames themselves? It is from the inevitable, unstoppable gap in time between the fire dying and a human being arriving to turn off the very technology that saved the building. Next time you look up at that little metal disc on the ceiling, you will know exactly what it is waiting for and exactly what it will take to make it stop.